Hello, Vital Sign. Today we're going to talk about network centralization measures. Network centralization measures are an attempt to quantify the intuitive notion of centralization in a network. Intuitively, a network is centralized if one node is much more important than the others. If we define importance to mean number of connections, this would mean that one node has a higher degree than all the other nodes. Here are some examples of very centralized network structures, taking the importance of the node to mean number of connections. Notice that there is a vast difference between the degree of one node to those of the other nodes. On the other hand, a decentralized network is one where all the nodes are about equal in importance. Again, if we define importance as degree, then this would mean that every node has about the same degree. From the perspective of a social network, this could be a group where everyone is friends with everyone, and there is no one person that holds the group together. Or it could mean a group where everyone has the same or about the same number of acquaintances in the group. All that matters here is that every node is about equal in its number of connections, and this only matters because we define node importance to mean number of connections. There are other definitions of node importance, and I invite you to check out my video on centrality measures to learn more about these. The main thing to grasp about decentralized networks is that they see little, or at least relatively little, difference in importance between nodes, however it is that we choose to define importance. So far, centralization as we've defined it is a bit of a fuzzy concept. How do we quantify it? Well, first, we have to quantify individual node importance through what are called centrality measures, which measure the centrality or importance of a given node. The easiest centrality measure to work with is degree centrality, where we define a node's importance to simply be the degree of the node. Here is a list of some of the other centrality measures. For each of the centrality measures I've listed here, there's a corresponding measure of centralization for the entire network, but thankfully they're all based on the same underlying idea. So by grasping one, you'll quickly be able to understand any of the types of centralization. The underlying method is that once we have a way to quantify individual node importance for each node in the network, find the difference in importance between the most important node and each other individual node in the network, and then add up these differences. Once we've done that, divide that sum by the maximum possible such sum of differences for a network of that size, obtaining a number from 0 to 1, as the numerator will be somewhere between 0 and the denominator. This number will tell us how centralized our network is compared to the most centralized network possible with that size. We can represent this as a formula like this. Let's dissect this formula, as all it's really saying is what we just covered before. Suppose we have a network with n vertices and some centrality measure, that is, a measure of individual node importance, C. C is a function that takes as its input some node v sub I and outputs the centrality of that node. Now, suppose v sub star is a node that maximizes this function. That is, it's the node with the highest centrality value in the network. Then C of v sub star is the maximum centrality value in the network. And this difference is simply the difference between the maximum centrality value in the network and the centrality of an arbitrary node v sub I. Now, this sum from 1 to n here means that we vary this arbitrary node v sub I on the right over all possible nodes in the network, of which there are n. And the word max here means that this entire expression denotes the maximum possible such sum for any network with n nodes. Without this max word, we would just be calculating the sum of differences in centrality for a specific network. This ratio, then, is what we call the centralization of the network, based off a given individual node centrality measure C. The numerator is the actual value of the sum of differences in a given network with n nodes. And the denominator is the maximum value of that sum of differences for any network with n nodes. Suppose we have 6 nodes and we're using the degree centrality measure for individual nodes, meaning that later on we'll be using the degree centralization measure for the entire network. What is the maximum possible sum of differences in centrality for any node in a network of 6 nodes? Well, this maximum is attained when one node is connected to every other node in the network, and all other nodes in the network are only connected to that node. The resulting graph or network is called a star graph. The star graph shown here with 6 nodes contains a node with the maximum possible sum of differences in centrality to all other nodes in a 6-node network. What is the sum of differences? In this case, that sum of differences is 4 times 5, or 20. Note that there's no other graph we can build on 6 nodes that contains a node with a greater sum of differences of centrality than the 6-node star. Generalizing for any n value, the maximum possible sum of differences of degree centrality for a network with n nodes is n-1 times n-2. It comes from the fact that the central node in an n-node star is connected to n-1 other nodes, meaning that this sum has n-1 non-zero summons. And the difference in degree centrality between the central node and any other node is n-2, as the central node always has degree n-1, and the other nodes always have degree 1. So that's our denominator. And the numerator is simply the sum of differences in centrality between the most central and every other node in the specific network that we're calculating the centralization of. Let's do 2 short examples now. What is the degree centralization of this network? Feel free to pause the video and work it out yourself. Here's the calculation process with the formula for degree centralization in the upper right-hand corner. To get our numerator, we need to find the sum of differences in centrality for our network. The most degree central node in our network is this one, so this is V sub star. There's our numerator. Now for our denominator. We have 9 nodes, so n-1 times n-2, which is our denominator, is 56. The degree centralization of this network then is about 0.36. How about this network? What is its degree centralization? Here's the calculation. To get the numerator, we need to find the sum of differences in centrality of our network. This is the most central node, so it's V sub star. Our numerator is 4. Now for our denominator. Our denominator is n-1 times n-2. Since n is 4, our denominator is 6. The degree centralization of this network is about 0.67. To summarize, the intuition behind centralization measures is that we take the most centralized network possible with respect to some centrality measure and find out how centralized a given network is in comparison to it. And we do that by first finding the sum of differences between the most central node and all the other nodes in the most centralized network possible on n nodes, and then dividing this sum of difference between the most central node and all other nodes in our given network by that value. That's it for this video. In my next video, we'll examine fractional colorings of graphs. Thanks for watching. Don't forget to subscribe, like, share, and comment if you liked the video. Have a great day.